Good day everyone, my name is Graphics. Today we'll be looking at steady flow energy equation. We know that a flow process or a flow of mass or a flow through an open system is what we call a flow process, right? And we know that an open system includes a large number of vertical devices through which a mass of fluid flows on a continuous basis, right? So when the flow of fluid remains constant, it's said to be what? A steady flow. Now let's consider these forms of energy and let's see how they flow through some of these devices. Now one of those devices that we have, one of those forms of energy we have is called the potential energy. The potential energy, right? We have the potential energy. Another device we have the kinetic energy. We have the internal energy. We have what is called the displacement work, because the fluid is flowing. The displacement work. We have what is called the heat transfer. And what is called the work transfer. Right? So these are the forms of energy that flows in a system. Now, for potential energy, in terms of extensive, when we say extensive property, we mean that a property that is dependent on the magnitude of mass. So we have the mass times gravity times the atom. This is the height above the reference point, right? Now we have what's called the kinetic energy, which is giving us the half mc squared, because the m here is the mass, the c is giving us the velocity. Now the next one we have the that is the internal energy, displacement work, which is giving us mpv, then the heat transfer, which is giving us this. Then we have what is called the work transfer, which is giving us what? This. Very good. So in this case here is in terms of what? Intensive property. In terms of extensive property. But in terms of intensive property is that what? We are not going to include the mass, because we know that intensive properties are properties that are independent of the magnitude of mass. So in terms of intensive property, we'll be having the gravity times the datum. We have the half c square, we have the u, we have the PV, the pressure and volume, then we see have the Q12 and we have the W12. So don't forget, this is in terms of extensive, this is in terms of intensive, which is per unit mass, right? Now, when the fluid flows through, when a liquid flow through a pipe or a system, we have what is called the inlet section. We'll call it the entry. In the inlet, it means all this flow will continue. So we have then the potential energy, GZ1, because of the inlet, plus the kinetic energy, half C1 squared, plus the internal energy, which is what? U, plus the displacement work, which is what? It is U1, which is P1, V1, plus the heat transfer, which is Q12, plus the work transfer, which is W12, right? Now, this is the inlet. Now this will now give me equals to what? The outlet. Now when they start flowing, I'll be left with my GZ2, that is at the point 2, this at the point 1, point 2, plus half C2 square plus U2 plus P2 V2. Now this is what we'll be having. The heat and the work will not be included because they are transitional energy, they cannot be stored in the system, right? So this you see here is called my energy steady flow what? Energy equation. This is my steady flow energy equation, right? Per unit mass. But in this case, sometimes we might not be given the internal energy, the pressure and the volume. So we need to know that both U plus PV is equal to what? Enthalpy. So when I'm not given the pressure and the volume, I'll say that my GZ1 plus half C1 square plus, so I'm writing these two, I'm going to put H1 plus Q12 plus W12 is equals to the GZ2 plus half C2 square plus, so I'm writing these two, I'm going to put H2. So this is still the same thing, but in this case now enthalpy, and enthalpy is given, right? So these are the two. So this is my steady flow energy equation when pressure and volume is not given, and when pressure and volume is not given, that is enthalpy is given, right? So we would like to take this example and we'll see how we can apply this energy equation. Now let's take this example. The example says that 0.45 kilogram per second of steam enters the steady flow turbine at the following states: pressure 3.0 bar, specific volume 0.0905 meter cube per kilogram, internal energy 2845 kilojoule per kilogram, and velocity 40 meter per second. Full stop. The steam leaves the turbine at the following states: pressure 0.5 bar, specific volume 3.420 meter cube per kilogram, internal energy to be 2512 kilojoule per kilogram, and velocity is 110 meter per second. Full stop. Heat is lost to the surrounding at a rate of 6.5 kilojoule per second, neglecting any change in potential energy. Determine the exit pipe cross-sectional area and the output power. Now what you do is that the first thing you write out what your parameters, right? So let's start. Now the first parameters we are going to write here will be this. It says 0.45 kilogram per second of steam. That is a mass per second. So this will be our mass flow rate. So our parameters here, the data here will be our mass flow rate is equal to what? 0.45 kilogram per watt per second. Now the next thing is the of steam enters the steady flow turbine at the following states. So at the following state means at the inlet point. So at the inlet or the entry, let's call it the entry. At the entry we have the pressure P. So we call it P1 because it is at what? The entry. So P1 will be equal to what? 3.0 bar. Now when I convert 3.0 bar, it will be what? 3 times what? 10 raised to power what? 5 Pascal. Right? So if you convert it, it will give me, I can write it as saying 300 times 10 raised to power what? 3 Pascal, right? And Pascal giving us what? Newton per what? Meter square. So if I do that, this 3 times power 3 is kilo, so I'll be having 300 kilonewton per what? Meter square when I convert it. That again, because I can still write this 300 as saying 3 times 10 raised to power what? So 2 times 10 raised to power 3, because 2 plus 3 is what? Is 5. So now we move further. The specific volume is this, so the V1 is giving us what? 0.0905 meter cube per what? Per kilogram. Now we move further. The internal energy, that will be U1. U1 is giving us what? 2845 kilojoule per what? Kilogram. And the velocity, that will be, I will use C1 not to disturb my V1, and that will be giving us what? 40 meter per second. Now that is at the entry. So the next one will be at the exit, because it is still in leaves, so it will be at the exit. So at the exit, it still leaves the turbine at the following state: pressure 0.5 bar. So we're going to be having P2 to be 0.5 bar, right? So if you convert this to give you 0.5 times 10 raised to power 5 Pascal. That again, and we know that it's going to be giving us 0.5 times 10 raised to power 2 times 10 raised to power 3 Newton per what? Meter square, because Pascal is in Newton per meter square. Now this is 10 per 2 is 100. 100 times 50 times 0.5 give you 50, right? We have 50 Newton, 50 kilo Newton per what? Meter square, because 10 per 3 is kilo. And this 100 times 0.5 will give you what? 50, right? So we move further. Now the next thing it's telling us here is that the specific volume is 3.423. So my V2 is equal to 3.423 meter cube per what? Per kilogram. Meter cube per kilogram. And the next thing here is giving us the internal energy is 2512. We'll have U2 to be equal to 2512 kilojoule per what? Kilogram. Now the next thing here, and the velocity V2 is 110 meter per second. So V2 is equal to 110 meter per second. Now if you look further, we say the heat is lost to the surrounding at a rate of 6.5 kilojoule per second. So in this case now 6 is at the rate of, so that will be my heat rate. So the heat rate is giving us what? 6.5 kilojoule per second. But since the heat is lost to the surrounding, I will introduce my negative sign here. Now if you look at it, we have to neglect any change in potential energy. So that means any change in potential energy, write potential energy. Potential energy is what is neglected, right? So potential energy neglected. So this is how we go. So that will be what 0. Now from here we move further to we want to start. Now what you need to know is, only we are given this now. Since we are given this, we now are applying steady flow energy equation. But before that, we know that recall my heat rate is equals to the mass flow rate multiplied by what? The heat transfer. So from here, my heat rate is giving us minus 6.5, right? equals to the mass rate is given as what? Our mass rate here is given as 0.45. We're having 0.45 multiplied by Q12. So if you make the Q12 result of formula, we are going to be having Q12 will give me minus 6.5 divided by what? 0.45, and this will give us, I will say 6.5 divided by 0.45, only 14.44. So we're going to write 14.44 kilojoule per kilogram. Is that okay? Now we've gotten our Q12. So the next thing we're going to do is, so the first thing we should do here is to calculate this. So we should calculate the exit pipe cross-sectional area. So in calculating the exit pipe cross-sectional area, let me do that here. In calculating the exit pipe cross-sectional area, we should say that for my mass flow rate is equal to what? The area times the velocity over what? Volume. But since it is the exit is always given the subscript 2, right? Because if I have a turbine, the inlet is 1, the exit is 2. So what I will do is that I will say that my mass flow rate will now be equal to what? A2 C2 over what? V2. Providing with the exit, it is the inlet or the entry to be A1 C1 and what? And V1. So for me, my mass flow rate is given as 0.45. So I'm going to input my 0.45 here. So I have 0.45 equals to the A2 multiplied by C2. The C2 is given as 110 times 110, right? All over what? The V2 is giving us 3.423. So if I cross multiply, it will be 0.45 multiplied by 3.423 divided by what? 110 is equals to what? A2, right? So my A2 here will now be giving us 0.45 times 3.423 then divided by 110. So my value here will now give me 0.014 meter square. Let me do that. So this is my exit cross-sectional area. Now for the 2 here, we are told to calculate what? The output power of the turbine. Now we know very well that the output power of the turbine is giving us output power of turbine. So the output power will giving us our work rate equals to what? The mass flow rate times the work transfer, right? So we know my mass flow rate, but we don't know my work transfer. So that applying steady flow energy equation, right? So we have this. We apply this equation here, the energy equation. Now we are told earlier that we are to neglect the potential energy. If you look at the equation, it says neglect potential energy, right? So since potential energy is neglected, you write since potential energy is neglected, since potential energy is neglected. So it means that I'm going to remove this and remove this, right? So I'll be left with 1 all over 2 c1 square plus u1 plus p1 v1 plus p1 v1 plus q12 plus w12 equals to 1 all over 2 c2 square plus u2 plus p2 v2, right? So from here I want to collect like terms, so I want to make my w12 the soluble formula, so I move everything this side. So if I leave my w12 here, w12, right, so this will come to the side, so we have 1 all over 2 c2 square minus 1 all over 2 c1 square. Can I see that? So move forward into the bracket plus this will come here, so to be u2 minus what, u1, right? So plus this will come to this side, we have p2 v2 minus p1 v1, right? So then this will come here, minus q12. So if you factorize this, my w12 will give me what is coming here, 1 over 2. So I'll be having c2 square minus c1 square all over 2, right? Plus u2 minus u1 plus p2 v2 minus p1 v1 minus q12. So let's start inputting our value. So inputting the value that we have here, my w12 equals to, the c2 here is giving us 110. If you check your parameters, 110 square minus c1 is giving us what, 40 square all over what, 2. But because velocity here this is for velocity and this is given meter per second and all our unit is in kilo, so we are going to multiply by 1000, right? So plus my u2 is giving us 2512 minus u1 is giving us what, 2845, right? So let me just put them in bracket here. So plus p2 is giving us 50 and velocity v1 is giving us what, times 0.0905, right? So we have this minus p1 v1, so the p2 is giving us what, 50 and the v2 is giving us 3.423, sorry, this will be giving us what, 3.423. So minus, we have p1 v1, the p1 is giving us 300 times my v1 is giving us what, 0.0905, right? This is what we're having here. So minus q12 here, which is minus the q12 is giving us 14.44. So I have found it to be a negative, because negative is also like a negative here. So into bracket 14.14 here. Bracket 14.14. Are we good? So if we continue from here, if you multiply this, 110 square will give us 110 square is going to give us 1200 minus 16, right? This is what we have here. If you multiply 110 square, we will have 12,100. 40 square is 1600 divided by 2000 plus 2512 minus 2845 will give us minus 333 plus 50 times 3.420 will give us 171 minus 300 times this will give us 27.15. So this 14.4 has a negative sign here, so minus will give you what? Plus 14.14. So this will give me plus 14.14. Right? So by the time you add everything, we're going to be having so let's do that and see. If we add them, we're going to be having this. Right? So let's see that. W12 will give me 5.25 minus 333 plus 143.85 plus 14.14, and that will give us 169.76. So we have negative 169.76, that's W12, right? So from here, we now say that recall our power will be the work rate is equals to what? The mass load times W12. So my power here will now give me mass load is 0.45 multiplied by this we have minus 169.76. So my work rate now will now give me let's see that so times 0.45 minus 6.39, so we have minus 76.39 kilojoule, right? And this is in what? In kilojoule by what? That's kilojoule in what? In watts, because it's power. So this will be our watts here. That again. So since it's in kilo, so to be what? In kilowatts. So I can see that the power minus 76.39 kilowatts. So that's our answer. So thank you for watching. Meet in our next video.